Everybody. My name is Dr. Laura Lahala, and this is my service dog, Wade. Um, I am the assistant department chair and also an associate professor in mechanical engineering. And my office is in the main ME office, which is on the first floor of the Engineering Technology Center. My office is Q131. So today I'm going to talk to you about the two programs that we have the two programs we have in mechanical engineering are mechanical and aerospace engineering. And this video is going to be about mechanical engineering. Maybe you can go by that. Oh, and he's got a pretty sweet setup back there. You can see she's got her bag that she likes to sleep in, and then she's got her bed over there. She's got a personalized mat and some water behind it. Hey, man, why don't we go sit down? All right. Okay, and into the bag she goes. There we go. Okay, so let me share my screen and I'll get my PowerPoint going. It's all right. And here is the PowerPoint. All right, so Department of Mechanical Engineering, see there's a QR code there for our department, or you could just Google Mechanical Engineering, Kennesaw State. Okay, so what I'm going to talk about in this lecture is the department. We're going to talk about what ME is, the branches of it, the curriculum, an example of a senior design project. We'll talk about employment, undergrad research opportunities, and the professional societies and competition teams. All right, so first about the department. So this shows, this is maybe like a third of our department. And here I am in the center, and this is my husband, Dr. Rich Lahala. We were two of the first three founding faculty for the department. The third person, Dr. Ray, has retired. And let's see, this is Dr. Al-Height. He was our department chair. I need to update my picture. Now our department chair is interim department chair, Dr. Supal, office manager, Holly Davis, and Aisha Tekis. Dr. Tekis created one of the videos, created a little of the content that I'm going to be showing you. And Dr. Supal also helped with some of the content. Okay, so again, the programs that we offer are bachelor's degrees in mechanical and aerospace engineering. Aerospace engineering offers two concentrations, concentration in aero and also astronautics. So I'll be talking about that in the next lecture. And also we offer a master's of science in mechanical engineering. Okay, so let's talk about the enrollment. So a lot of students don't know that up until August of 2009, so not really that long ago, it was illegal for any state university to offer engineering except Georgia Tech. I don't know how this law came about. I think there was some sort of backroom handshake discussion 100 years ago. So the problem with that was that Georgia Tech just could not produce the number of engineers that the city, the state, the region, and the country need. And so at that point, three other schools were allowed to start engineering. So obviously one is Southern Poly, which became Kennesaw State. Do you know what the other two are? Other two schools where you can get engineering, other than Georgia Tech and UGA and Georgia Southern. So in August of 2009, UGA and Georgia Southern were both, as well as Southern Poly, got permission to start engineering programs. So our engineering programs are all the same, have the same start date. They're all the same, have the same history, they're at the same age. So when we first started out, as I said, it was me, my husband, Dr. Rich Rahala, and Dr. Maid. There were three faculty members, and we had 35 students. That was in January of 2010. By 2011, we had 321 students. Still three faculty. We were hiring faculty. And then by 2014, we got ABET accreditation and our numbers went up. So what is ABET? ABET is the accrediting board for engineering and technology. And every engineering program in the country, and frankly, all of the major ones in the world are ABET accredited. This is just for undergraduate engineering. So if you go undergraduate mechanical engineering at virtually any accredited school in the world, you will be studying the same topics to the same depth. ABET does not cover graduate programs. The graduate programs can vary more, but undergraduate programs, it's always the same topic and to the same depth. Let's see, so we got ABET accreditation in 2014. You have to have a graduated class before you can get accreditation. So the students that first started off, they started off just kind of on a promise that we will get accredited. And then once you get accreditation, it is retroactive to any previous graduates. So once we got accreditation, as you can imagine, the population really grew. This is just enrollment in mechanical engineering. 2017, we hired a lot of people. Most of the faculty that we hired have industrial experience. We thought it was very important that we hire engineering professors who have actually worked as engineers. And there was a big focus on that. And now we have, as of 2024, so as of, I need to change that, actually, as of 2025, we have over 2,700 students. So it is by far the largest department at Kennesaw State. And as a matter of fact, it is the 5th largest mechanical engineering department in the country as measured by the number of undergraduate students. So it is enormous, starting off just 15 years ago, January of 2010, with 35 students and 3 faculty. Now we are 5th largest undergraduate engineering program in the country. Yet we have small sizes. Now, you wouldn't know it from ENGR 1000. That's a real anomaly because it has big classes. But the class sizes are limited to the rooms. And if you go around the Engineering Technology Center, where most all of your mechanical engineering classes will be taught, you'll see that almost all of the classrooms are maxed out at 40. There's maybe 3 or 4 rooms that go up to 70. There's one huge room, Q202, that has like 200 students, but we don't teach mechanical engineering classes in there. It's too large. So we have small class sizes. Most of the lab courses, we will have no more than 20 students. We have outstanding senior design capstone courses, a whole bunch of internship and co-op opportunities for ABET and SACS accredited, and we have experienced faculty with research experience and national research awards. So before Rich and I came to, I guess I should have said, before we came to Southern Poly, we were at University of Southern Indiana, where we also had started up a brand new engineering program. And so, so we were very excited to do it again at a good school like Southern Poly, now Kennesaw State. Okay, let's see. So what is mechanical engineering? All right, so the one word I really want you to take away from this is broad. ME is one of the broadest engineering disciplines. Virtually any product you look at has been touched by a mechanical engineer. Just even the chair I'm sitting on. The chair I'm sitting on, mechanical engineers have been involved in. They would have designed the structure of the chair, the motion, and also gotten into the ergonomics and the manufacturing. So virtually every product or service in modern life has probably been touched in some way by a mechanical engineer to help humankind. MEs apply the principles and problem-solving techniques of engineering from design to manufacturing to the marketplace for any object, and even beyond the marketplace. Now we need to think of like the end life of products and hoping that we can reuse and recycle a larger percent of that product so we send less to the landfills. To meet the broad demand in mechanical engineering, they design a component, a machine, a design, or a process. Being ingrained in many challenges and innovations across many fields means the ME education is versatile. So to talk about versatility, let me I guess just use my own story, origin story, as a basis so you can see how versatile your career can be. So I grew up in Flint, Michigan, and General Motors is huge in Flint, Michigan. And they had engineering co-op positions. And I started doing an engineering co-op when I was when I was 17. So my senior year of high school, I had an engineering co-op where half the day I would go to General Motors, and I worked at General Motors. And then I worked at General Motors through the school I went to. I went to Kettering University. It has a mandatory co-op program, so it's a 5-year program because every other quarter you co-op. And I was able to get GM to sponsor me. So for all 5 years, so I continued working at GM every other semester, so 6 months a year. And then after graduation, so I hired in, and I hired in at a great salary. It sounds bad now, but I hired in. And Rich and I both hired in. He was a co-op as well. We got married right after college, so he also hired in. Remember this number: 35,220. So our salary was each 35,220, and which I know today's dollars it doesn't sound like much, but the new employees at GM that were coming in that hadn't done the co-op were making 28,000. Think about that, for the 20% more. And that holds true today. If you do co-ops and internships, you can hire in substantially more than your counterparts. And also, it's much easier to find a job if you have that work experience. We'll circle back to that a little bit later. So I was designing an exhaust joint for GM, and it was the joint just ahead of the catalytic converter. So it was an important joint because if it leaks, that would have noxious fumes that can get into the passenger compartment, and also, of course, can get into the environment, which is bad. But I worked on it for quite a while because my last year as a co-op, I did a honors project. I worked for 9 months on that joint. And then I, hired in, and they said, you're so good at that joint, we're going to keep you on that joint. So I started it, and then I really had a crisis of wondering, like, I just hated what I was doing. I was like, oh my God, did I go into the wrong major? I mean, maybe I'm not even intended to be a mechanical engineer. What did I do? It was kind of a crisis in my life. But then I realized, it's not engineering I don't like. It's this darn joint, because I've been working on a joint at that point, this one joint for like a year. I just pretty much did all I could do. It was kind of boring. So I changed positions within the company. So that's great. So I was able to maintain my salary, and I hired in with 3 weeks paid vacation, all the benefits and so forth. So I transferred to truck division and safety and crashworthiness engineering. And so I hope you don't mind just these little personal stories. So I remember when I hired him, I was interviewed by this guy, Mark, and he said, we're going full frontal. This was during my interview before I hired him, my interview. He said, we're going full frontal. And I didn't know what he was talking about. When I heard full frontal, I only thought like one thing, and it wasn't related to cars at all. And I thought, I hope he's not talking about that. I don't want to go full frontal. And so as I was patient, and I let, finally I figured out he was using a term of art. A term of art is something that when you're in an industry, it's just a term that everybody uses and everybody knows what it means. But outside of that industry, they don't know what you're talking about. So we're going full frontal. I finally realized that what he was talking about was we were going full frontal airbags. So before that, the cars had, so airbags were brought into the auto industry in stages. First, cars had just steering wheel airbags. And then trucks, a couple of years later, got steering wheel airbags. And then a couple of years later, cars went full frontal, meaning they had the airbag for the driver and also an airbag for the front passengers. And then the trucks followed a few years later. So this was the stage. And then, of course, then we went to side airbags and curtain airbags and all that. They progressed to now the technology is much more advanced than it was, and much more encompassing if you're in an accident like that. Oh, I didn't mention that I was when I was coming home from GM, the high school co-op, I was a sole survivor of a terrible car accident. And so that gave me a real appreciation for automotive safety. Everybody in my car died. It was awful, very tragic. Sometimes if you see me around campus, you'll see me in an electric scooter. It just means that I'm having some pain. And of course, I have Winnie, and Winnie has been trained to help me. She's specially trained, she's task trained, which helps me with my pain. Anyways, I have this chronic pain. So I had a real appreciation for automotive safety. By the way, I was the only person in my car that had my seatbelt on. The light tour. Okay, so what was I saying? So I really liked automotive safety. So I got the job, and I was very enthusiastic, and I got the job. And so I spent half my time at the tech center in Warren, Michigan, where I was doing crash analyses, simulations, so computer simulations, finite element analyses of crash simulations. And then the other half the time I was at the GM Proving Grounds in Milford, where I did the actual crash testing. And one of the things that was new to trucks going full frontal is that there's three cabs. You have the standard cab, the extended cab, and the crew cab. The crew cab has a full true back seat. So if you have you always think worst case scenario. So if you have worst case scenario, it would be a standard cab with no back seat. And what if you have a child? So you have to put a child in the child seat, of course. Everybody knows that. But you may or may not know that infants must ride backwards. So I'm not a mom. I never went through this with like my own children, but something about their neck strength, and otherwise, apparently a fender bender, they'll break their neck and die. So children always have to ride backwards. So the problem was putting a rear-facing car seat in the front passenger seat of the truck. And so that was one of the things that I was tasked with, is seeing what happens. And so, I had the full-scale crash test and dummies and stuff, and boom, and killed the kid. I mean, it was one dead kid. Really crushed the skull. And so I reported back to my boss and said, it was not good. And he said, we need to try it again. So I tried it a few more times. These were all with prototype hand-built trucks. At the time, they were $250,000 each. And now, that was when I was making like 35,000. So it was a long time ago. So this was in, when was this? This was in 93. We were designing the truck, the CK truck, the full-size truck that was supposed to be released in 99. It actually was released in 2000. It was the later year. So I tried it again, and boom, boom. It was kind of gruesome. There is no way that infant is going to survive it. And so afterwards, the people would rush over, literally in white coats, rush over and look at the infant, and then they take it. There's a dummy hospital. I don't know if you know this. At least at GM, there's a dummy hospital, and they would take it in their white coats. They take it. And I never knew what they did with the dummy. My suspicion is that there was a reset button in the groin, and all they had to do is pop it and reset it. But I guess it's more complicated than that. There certainly are complicated devices, these dummies. But anyway, GM had a real problem that what if you have a kid and you have an infant that has to ride backwards and you don't have a back seat? This is the first time this problem has really been presented to the auto industry. So we had this big meeting, and the vice president of GM was there, vice president of safety was there. I gave my presentation, and it's clearly not survivable. It will crush the skull of the infant. These airbags were really powerful because they were designed for unbelted occupants. So that's also something to keep in mind. Back then, that was before there were real uniform seatbelt laws. And so these older technologies were designed for unbelted occupants. So they had to be more aggressive because the occupant would get there faster. So that's just something to keep in mind. But even now they're very powerful, as you may know if unfortunately you've been in an airbag accident. So I gave the data and, clearly this is not survivable. And I suggested, and they said, what do you think? And I said, well, I think we need to have an on off switch. And everybody in the room started to laugh. Well, even my buddy Tom was laughing. Oh, he heard about that later. Everybody started to laugh. To this day, it is my most awful, humiliating professional experience of my life. I flushed really red and they all laughed at me. And what was so funny apparently about what I said is I had not considered the Insurance Institute and whether the Insurance Institute would allow something like an on-off switch. And you know what? Right? I hadn't considered the Insurance Institute. I hadn't even heard of the Insurance Institute. I was just thinking about these, infants. So I sat down and they all discussed, and I didn't open my mouth for the rest of the meeting, as you can imagine. And I was a young engineer too. So I didn't talk for the rest of the meeting. So then they decided what they're going to do. Their official recommendation was this. If you have a baby, you need to drive your other vehicle. Everybody seemed happy and they left the conference room. And so then I talked to my buddy Tom afterwards, and after yelling at him for yelling at me for laughing at me, which was not cool. I said, what do you think I said? What's the problem with just drive your other vehicle if you have a baby? What if you don't have another vehicle? It's a big problem. And also, will the person know how critically important it is that you not have the infant in that car seat, in that front seat? So the whole drive your other vehicle. But are people really going to heed the warning? Even if they do have another car, are they always going to be able to heed the warning? That's not going to happen. So I went off to graduate school, and we're still friends today. He called me about 6 months later, and we talked more frequently than that, but about 6 months later, he reported to me that they changed it, and they are now going to have a key that's an on-off switch. So there's a special key. If you get the car, there's a special key. But the only people that will have the key are the dealerships. So it was better, right? Because at least you can turn it off. But you have to take your vehicle to the dealership. They're going to charge you $100 to do that, just for a mechanic to go in and flip a switch with the key. So I was like, well, that's better. And then when they ultimately released the truck, what they did is they changed it so there's still a key, but they gave it to the consumer. So when you bought your car, you got your keys, it came with this on-off key for the airbag. So that was what they ended up doing. And the first generation of full frontal bags, that's in trucks, that's what they did. So what do they do now? Because this is a big problem. What do they do now? The problem hasn't gone away. You still have standard cabs with a potential car seat, and specifically an infant carrier that's riding backwards. Well, now they have sensors, and that's so much better. Another thing that's good about a sensor, obviously not killing infants is the number one thing that's good about it. But another thing is that short people were having problems. Well, the short drivers, that was another thing they had to work on. That was a whole other issue. But so infants, it's good for, and also the sensors are good if you're in an accident and you don't have somebody sitting in the passenger side. You don't want the passenger side bag to blow for several reasons. It's bad for your hearing, number one. And number two, it's really expensive to have it replaced. So say it blows for no reason because there's nobody sitting there. Then if if you can, fix the car, you have to replace the airbag, and it's super expensive. So that's what they ended up doing. So after that, I went to graduate school. And when I was in graduate school, I studied impact um, of composite plates, specifically with airplane wing, um, impact of airplane wings. I went to Penn State, and so I wanted to do something with impact because I really loved, this working in safety and crash worthiness. Like I fell in love with my mechanical engineering. It was funny how I needed the right application, an application that I found interesting and not like that same old joint. Um, so I uh, worked on impact of airplane wings, looking at low velocity impact. This is the type of impact you get from a bird strike or from runway debris getting sucked into the wing. That's actually what got found the Concorde. I think it was at 99. So it was at Penn State for 5 years. I got my doctorate. And then after that, I was a professor, assistant professor at Lafayette College. That was not a good fit for me. I was there for 2 years. And then I went to Pride Mobility, and they make electric scooters, electric wheelchairs, and lift chairs. A lift chair is like a recliner, but if the person doesn't have the strength to get out of the recliner and stand, it takes them to a standing position. My parents have a wheelchair. In their old age, they can't get out of a seated position by themselves. So yeah, so I did that, and then I went to USI. And when I was at Southern Indiana, I designed an orthopedic plant um, that was used for lower leg trauma. So I got into biomechanics. And it was used for lower leg trauma. It's called damage control fixation. So it'd be for like lower tibia fractures, and it goes around and it stabilizes the fracture. And that was in 2007. And we were fighting wars on two fronts in Iraq and Afghanistan. And the soldiers were getting just blown to bits by IEDs. And the IEDs, if the soldier survived, they cause terrible lower leg injuries, as you can imagine, because it kind of is a blast from below. And so this clamp was used to stabilize fractures for either for patients that aren't stable enough to have the big surgery to redo. These are big, major fractures, the surgical repairs needed. So either the patient isn't stable enough to have the big surgery, or they're not logistically in a place that they can have it. And back then, if you were in Iraq, you had to be, say, air back to Germany before you had the big, that was back then, before you have the big surgery. And so this was to stabilize fractures. And it's funny, my mom ended up falling, and she broke, just a stupid fall. It was just, it happens to older people. And she broke her tibia and ankle just really bad. And they ended up using this external fixation, and they used my clamp. So I was with her in the hospital, of course, and they put it on. I couldn't believe that was my clamp. So it was really amazing having my own mother benefit from a clamp that I know was safe and I got it FDA approved. I worked with an orthopedic surgeon on that. Let's see. Then got the program started at USI, and then Rich and I came to Southern Poly, now Kennesaw. And while here we've been studying, we do our research together. We really like working together. We've been studying acoustics, which is his thing, and I've been gotten into that, and he's gotten into biomechanics, which is more my area. One of the things we studied was hair pulling in athletics, specifically football. We love college football, go Penn State, go Michigan State, go Kennesaw State. And we noticed that the players, their hair, their hair got so long, and we were worried about hair tackles and what would happen if you had a hair tackle. And so we studied that and worked with Troy Polamalu. You might know he was a strong safety, maybe you don't know. He was a strong safety, probably Pittsburgh, from Pittsburgh, the Steelers. Um, And so that was kind of interesting. And then most recently, we worked on face mask acoustics. And then I also research engineering pedagogies, which means teaching engineers most effective ways to teach engineers. I've been involved in that too. All right, so my career has been very versatile. Just with my ME, I can go into so many different areas. I can change the application, but the engineering is really the same. So that's why I told you this story, is because I wanted you to see how really versatile a mechanical engineering degree can be. And I think it's that versatility is what makes it so popular. Back to the PowerPoint. Okay, so this is looking at undergraduate enrollment and bachelor degrees awarded. Looking at both of those measures, and ME is just second to none. It is very popular. Again, I think the reason it's popular, one of the reasons is it's so versatile. And we'll talk about where some of this versatility comes from in just a minute. Return on investment. Gosh, there's really for any of the programs in the college, the return on investment is great. Our mechanical engineers are starting off between 75 and 80,000 a year when they graduate. So yeah, it's really good. Increase in demand. So as you go on, there's been increase in demand. And as you go on, you make increasing salaries. So which is what you would hope. As you get more expertise, you should make more money. And so there's a lot of need for mechanical engineers. Okay, so if you think about, now let's talk about applications. If you think about mechanical engineering, say like, for example, you're putting together a PowerPoint for the ENGR 1000 class and you're Googling mechanical engineering, what I did. Something like this might come up, where people think about gears. They think about like gearheads and mechanics and automotive. That's kind of, I think, where the mind goes when you think mechanical engineering. But ME is much broader than that. Yes, it is these machine elements. It's a big part of ME. But it's not the only application by far. You can go automotive. Most all of my friends in the auto industry, and I have quite a few friends and family in the auto industry from Michigan. Most all of them are working on EVs. Rich and I just got our first EV. We got a Mustang Mach-E. Love that vehicle. It's my favorite vehicle we've ever had. So there's the EVs. You can go into aerospace. A lot of EVs go into aerospace. HVAC. So HVAC stands for heating, ventilation, and air conditioning. And so all HVAC and is a section of ME. And what we're finding now is that there are so many data centers being built that HVAC is a really important consideration with data centers to keep the crews cool. Oh, here's just showing. I thought that was kind of cool, showing thermography of a house. You could work designing a wind turbine. As a matter of fact, we had a student who did a co-op with a company that designed wind turbines. And he went to the career fair because when I teach the lab, I get extra credit if you go to the career fair. There's 2 career fairs. I guess, well, I'll talk about those when I talk about internships. But anyway, he did a co-op. So a co-op is where you do essentially an internship every other quarter, every other semester. So you go to school, then you go to work full-time, then you go to school full-time, then you go to work full-time, school full-time, work full-time. It's 3 rotations at the company. And so my student did this and he loved it. So he reported back after his first semester. He's working for this wind turbine, huge wind turbine company just north of Atlanta. And he loved it there. He was like, they had his first semester, I think he had just finished his freshman year. They had him like moving parts from one facility to another, like, pickup truck and doing different things like that, kind of some grunt work. But he was all over the facility and he just loved it. He didn't really do engineering per se, which makes sense because he wasn't really an engineer. And same with me. When I started working in engineering co-op in high school, they had me like filing and stuff. which I remember complaining at dinner one day that, I didn't complain at work, but at dinner, I was like, we're not having to do engineering. Never forget what my dad said. He said, what do you think you could do? And I said, well, true. So when you start an engineering cooperative internship, they know that you've just finished like your freshman year. Like they get it. And so they don't have you engineering an entire HVAC system because they know you've never had that class. So they give you knowledge appropriate skill jobs then as you go back, they give you more and more engineering. So this happened with Scott. So his first semester, he loved it there, kind of grunt work. His second semester, they actually had him doing some engineering. So at that point, he knew more. And then his third rotation, they had him do more engineering, absolutely loved it. And they flew him to Germany, all expense paid, of course, to Germany. He was there for a couple of weeks. It's a German company. And they wanted him to see the German place, and he was working with engineers there. They did speak English, I asked. So then after graduation, he got a really sweet job offer. I mean, much more than other students were making from this wind turbine place. But the catch was that they wanted him to move to Germany for a few years, and then he could relocate back to the US and probably Georgia, where he wanted to be. And he was engaged at the moment, and his wife was a elementary education teacher. She just graduated herself. He got married right after college. And so they didn't want to relocate. They didn't want to go to Germany. They really wanted to stay close so that she could do her teaching and stuff. So he turned down that job, but he was able to parlay the offer into a job at a roller coaster company. So yes, there is a roller coaster company in Atlanta. So he worked there. So he was able to get the roller coaster company to match the offer he'd gotten from the wind turbine place. So that's smart. It's very smart. And he loved working at the roller coaster company, and it was local. So his wife could, she got a job locally as well as a elementary school teacher. So it worked out very well. Okay, so other applications that was diverged here. You could work in construction, so you wouldn't necessarily design the dam, but you can design equipment that builds the dam. I guess mechanical engineers are also involved in the dam. That probably would be more civil. Biomechanics, certainly. Biomechanics, prosthetics, that's all going to be, I think this picture is fake, but I thought it was kind of cool. And sustainable energies. So you work in sustainable energies as well. So you don't have to be an environmental engineer to work in sustainable energies. Okay, so evolution of design. Every once in a blue moon, you might get lucky enough to work on something brand new nobody's ever done. That doesn't usually happen. Usually what it is, it's you're in an industry and you're going to the next generation. And so you are like standing on the shoulders of engineering giants, and you're taking it one step further. As an example, you can think about, for example, how so many of my friends are working on EVs in the auto industry. I have some people that are working, I know some people, of course, are still working on internal combustion engines, but a lot of my engineering friends are working on EVs. And so you're not designing a car, the very first car, but it's the next generation. Same thing with flight. It's going to be a next generation type thing. If you think about even like working on a washing machine, think about how that technology has changed in like 100 years. So it'd be the next evolution. And then also I have an example here of evolving technologies for sound. All right. So the mechanical engineering process, it's pretty much like the design process, mechanical engineering design process. First, you start off with design. And yes, that includes CAD. And so for sketching and CAD, and then analysis. So you analyze it. Is it doing what you think it should do? And then you go back to design and you change it and you go back and you iterate again and again. Okay, then once you get it, then you go to like full scale testing. And then if you find something like it's not working, you scoot back to design and then, so it's an iterative process. And then finally you optimize. And that is basically the like ME design process. Okay, now we're going to talk about the branches of ME because there's three kind of distinct branches of ME. There is mechanics, thermal fluids, heat, and systems controls and vibrations. So as an undergrad, you will take classes in all of these areas. And then through usually through the job you take, that kind of dictates what your specialty becomes. But you can change, you can change, like if you're working in, like, say, HVAC, you're like get tired of HVAC, you could change to working in mechanics or working in vibrations. You can, but often people with their jobs, they get more and more depth of knowledge through their experience, and then also graduate school, if you go on to graduate school. So my area became, so I had classes in all these areas, but my area became mechanics. And largely because I realized that I really like breaking things, killing things. I really like breaking things. And so that's why I like mechanics. Okay, so we're going to first talk about mechanics. So mechanics, you can think structural mechanics. There are MEs that design bridges, highways, superstructures, and stadiums. You might be a little bit surprised by this. You might think, oh, that's going to be bridges and highways. What do you think? Civil. Well, yeah, there's overlap between civil and mechanical. There's overlap between mechanical and electrical. There's overlap between mechanical and systems. The engineering disciplines, there is overlap. So yeah, so to design bridges, you need civil engineers. You also need mechanical engineers. Same thing with highways, superstructures. You can go into aerodynamics. That is an application of mechanics, obviously going to be used in aviation, but also automotive, wind turbine, aerospace, electronic, thermal management. And then machine design. So machine design is what a lot of people think when they think of ME. So it's like nuts and bolts. So you can design gears and disc brakes and engine components. So if you want to do that, that's a branch of mechanics, which is an area of ME. Then the next area that you'll be learning about as an undergrad is thermal fluids and heat. Now, as I say, I had all these classes, but I haven't worked in the field for a long time. So I asked my colleague and buddy, Dr. Gerald Pappen, to please create some slides. And I said two things, like, what is it and why do I care? So he was kind enough to give me these slides. So what are thermodynamics and heat transfer? So thermo deals with energy transfer, work, and heat in systems. Heat transfer involves the movement of thermal energy between regions of different temperatures. And that happens through conduction, convection, or radiation. Why do we care? Well, thermal and heat transfer drive efficient energy conversion. And that is really important if you are designing anything like an engine or a turbine. Okay? Also, it enables precise temperature control, which is crucial for a system's performance and durability. You can apply these principles to heating and cooling and HVAC systems. Right now, so many data centers being built, and they have our ME interns doing the ventilation as well as the structures as well. And then also material science also relies on thermodynamics as you choose optimum thermal properties. So that's thermal fluids and heat. The third branch is systems controls and vibrations. And I asked my bestie, Dr. Alicia Tekis, to please help me with this section of material. And so she gave me this, starting off with this quote from Tesla, Nikola Tesla. All right, so here are some examples of rotating unbalance that can cause undesirable vibrations. Now, undesirable vibrations can absolutely lead to failure. This is an everyday phenomenon we see in life. So if you look at the center right here, let me take this back just a little bit. See how it's spinning and there's no vibration. The vibration occurs laterally. So that means that the system is balanced. Now Dr. Takis is going to put a single mass in here. Now you can see the system is not going to be balanced from a weight standpoint. So, as you might expect, there's going to be vibration. See how it vibrates. Okay, so we see the vibration. So now Dr. Tech is going to add a second mass. It's going to twice the mass. So you might think it'll be twice the vibration. But see how she's balancing the mass? So it goes back to no vibration. And then she'll put on a third one, and it'll vibrate, and then a fourth one, it won't vibrate. So these are kind of examples of what's going on here. And she has a really awesome, we have an awesome dynamics and controls lab, and she has an awesome research lab as well. Okay, so this is, okay, so why should an engineer want to know the natural frequency that's the part of vibrations of the system to prevent failure? Vibration analyses can save your design. And I really appreciate this video she put together showing simulations you can do that show the vibration and so forth. This is all awesome. But when I think of natural frequency, one example comes to mind that is just really telling. It is the failure of the Tacoma Narrows Bridge. And this happened in, I think it was 1939. And so let's watch that video. Okay, so here it is after the collapse. Spoiler, it collapses. So I'm going to play this. So this is an actual video of it's actual film in a newsreel that was released. I guess it was released in 1940. Now look at the bridge. So this is in Washington State. Look at the bridge. Do you see how like elegant and almost modern the bridge looks compared to its predecessors? For the predecessors, think like the Brooklyn Bridge. This was built, I think, in 1939. And for the predecessors, think the Brooklyn Bridge. But this bridge had a real problem. And we'll see that the wind was only going at 35 miles an hour. It's not a hurricane that went through here. The wind at 35 miles an hour excited the natural frequency of the bridge, which caused these huge vibrations. And there was a fatality. No humans died, but this photographer who took a lot of this film, he left his vehicle in the center of the bridge. I'm not sure why. And he left his dog in the bridge. I think the dog's name was Beamer, and he was in the bridge. And that's not me. Okay, so prepare yourself. This is only like a minute long.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
My dog is awake and hoping she didn't catch what just happened. So this, they called this bridge after this happened, actually before it happened, they called it Galloping Birdie, because this wasn't the first time it started vibrating like that. It's like the girders of the bridge galloping because they're leaving. That is the effect of vibration on your structure. It's an undesirable effect of vibrations on your structure. Okay, so let's change, and we've talked about the branches of ME. Now let's talk about the ME curriculum. So like most of the engineering, you're going to start off with the fundamentals, math, science, and gen ed. In ME, your computer programming will be in MATLAB. This semester you're taking ENGR 1000. Next semester, if you want to go ME, you would take ME 1001 lab. Now remember, next semester you're going to take a lab in what you think your intended major is. If you decide that you hate it, so let's say you take ME 1000, I teach ME 1000. Take ME 1001 and you hate it. You know, oh God, I got to get away from this. So let's say you move to systems engineering or robotics, mechatronics, any one of them. Let's say you go to computer engineering. Computer engineering will accept the ME 1001 lab. So at the end of the first year, regardless which lab you take, as long as if you change majors, the new major will accept the old major's lab. So that's good. You don't get behind in the or take a class that doesn't ultimately end up helping you in accounting towards graduation. So for math, you take Calc 1, 2, 3, and 52. You take Chem, Quiz 1, Quiz 2, and then the other ones. Then you get into the engineering 4. So take a graphics class. Here we use SolidWorks, which is pretty much the industry standard to use SolidWorks. Then you take statics. Statics are the forces on objects when they are not accelerating, so they're not moving, not accelerating, and they're not braking. So like the force of my mouse as it sits on my table. I know you can't see my table, but you can imagine how it sits. Or let's say my printer. The force of my printer as it sits there on my table. It's not accelerating and it's not braking, but there are forces on it. Then you take dynamics and strength. It gets more complicated. You have to spend, it's not that you can't do it. You have to spend more time probably studying, but probably you're going to be more efficient at studying by the time you get to that point. Dynamics, things start to accelerate, and in strength, things start to break. And then you also take thermo and fluids. Then you take the ME core, computer data engineering, heat transfer, machine design, where everything now is like can be accelerating and braking, so kind of more realistic. Dynamics and vibration, machine dynamics and vibrations, manufacturing, material science, and then system dynamics and controls. And then your tech electives, you have to take 2 of them. There's a whole bunch of them to that you can take them from. We also have some minors that really work well with ME. The minors that make the most sense. So a minor is 5 classes. So, but 2 of them can count as the tech elective. So it ends up just being 3 extra classes. So it's not that big. And we have minors in aerospace, biomechanics, mechatronics, and nuclear engineering. So all 4 of those would really work well. You can get a graphics minor, but you wouldn't count as your tech elective. So it would be 5 extra classes. Same thing with environmental. I'll see. That's all I want to say. Oh, you can take an internship class. So once you have 90 credits in engineering standing, if you do an internship, you can take a class. Should I develop this class? And the class will count towards a tech elective. It'll count as a tech elective. So have that be one of the tech electives. So something to think about. Okay, and then the project. You do a 2-semester senior design project. So yeah, this is our before and how you feel after. Okay, let's talk briefly about an example of a senior design project. So we had a company in Arizona that asked us to help design a controllable airplane camera mount. We had one of our senior design teams do this under the guidance of Professor Roberts. And this is for general aviation. So they started off, as you might expect, sketching some ideas. Then they took them into CAD, and then they did analysis. And there were some places where the mount was not strong enough. There were other places where the mount needed to be beefed up. Other places where the mount was too strong. You might think, well, too strong isn't like the stronger the better. No, if it's too strong, that's also bad engineering. Obviously, it has to be strong enough. That's really bad engineering. But if it's too strong, that's also bad engineering because you're being wasteful. Either You can go to a lower grade material, or you can, in this case, get rid of some of the weight. You don't have to have as much material, which is really important, obviously, in this type of airplane application. And then you go to a better model, and then you do the prototype, and then they installed it, and there it is, folks. Right there is the camera inside. You can see the lower part of the wing. And here they have their animation, which is exactly like their prototype. Okay, employment, internships, and co-ops. So as an ME, there's just the sky's the limit as to where our MEs are going. You name it, we've got somebody there. We're a big program. And so again, internship. So okay, so employment for internships and co-ops. You will be paid. You're not going to be doing this volunteer gig where you shadow somebody for 2 weeks. I mean, maybe that's good, but you're kind of beyond that point. And in September and February of the year, there's a KSU STEM career fair. You'll see signs up, and you can Google it and see exactly when it is. It's 3 different days, and there's different employers all 3 days. Typically, the first day is kind of more electrical engineering, computer engineering, electronics. The second day is typically more with civil and construction management. The third day is more mechanical. So if you only go one of the 3 days, go the third day for mechanical. But it's from 11 a.m. to 3 p.m. And we use the app called Handshake to upload your resume and then to show it to different resume people, to different employers. Now, you should go to the career fair before you're desperate to get a job. Because, like, say you really want to get an internship, a paid oh, by the way, these are paid internships. I don't think I talked about it. Okay, so let's say that you really want to get an internship in May or a co-op in May. So February shouldn't be the first time you go to the job fair. You kind of want to get like the lay of the land and see there's a certain procedure you want to get familiar with. So go to the one in September and then go to the one in February. Ideally. And no, I don't think I talked about the difference between internship and co-op. They are both going to be paid and paid well. This last summer, I know that our average intern co-op was making $24.75 an hour, so it pays well. The highest was $52 an hour. That was an outlier. That was kind of crazy. So they're going to be paid, and they'll be full time. It'll be a full time job. An internship is a one and done. You do it for a semester, and that is all. It's full time, one semester. Co-op, you do it for full time for a semester. You go to school for a semester. You do the sequence: school, work, school, work, school, work. So 3 rotations of work. If you absolutely hate your job, you can get out of it. If they absolutely hate you, they can get out of it. You know, this 3-semester commitment. But that doesn't normally happen. That's extremely rare that happens. So yeah, everybody should. I know that you're probably thinking right now, how quickly can I graduate? And you're trying to fill up which classes you're going to take, and man, you're going to go in the summer too, and you're going to get out of here in 3 years, and yay. Well, it's not the way to go about this. You want to pause and work so you can see whether or not you like this field and get an idea for what area you might want to go into later. Also, you're going to be much more competitive when you're looking for a job after you get your degree. Think about it. Everybody has, if you're going for mechanical, everybody has the BSME. That is the minimum requirement. So if you have a BSME and an internship, or a BSME and a minor, if you're going mechanical, the math minor is just 2 additional classes. I ended up stumbling into that. That's one of the reasons I got that job in safety and fast working. That and my co-op are the reasons I got that job. It was very competitive to get in that A lot of people want to be in that area. Um, so yeah, so think bigger picture. It is not just a race to the end. That is really a short-sighted way to look at this. And then probably you'll end up going to graduate school later. I highly recommend that students work for a little while before they go to graduate school, unless you do the double OWL. I would definitely do the double OWL program. Somebody else will be talking about the double OWL program. That's when you get, you take your upper class courses, and they also count towards graduate school. That there's no reason not to do that. Okay, this is employment, internships, and co-ops. Now, research opportunities, there are lots of research opportunities in mechanical engineering, and there's all of these advantages to it. You can pause the video if you want to see, look at it closer. And ME and ME related professional societies and competitions. So the big ME related professional society is American Society of Mechanical Engineers. And everybody that wants to be an ME, or everybody, if you should join your professional society, the American Society of Civil Engineers, the IEEE, if you're going electrical or computer engineering, figure out what your professional society is and join it. It's either free for students or it's really cheap, and it looks so good on your resume. You don't have to be super involved if you don't have time, but obviously I encourage people to get involved. So ASME is the group, and then Rich and I are both co-advisors to National Fluid Power Association, their Society of Manufacturing Engineering, American Nuclear Society, and AIAA, which I'll talk a little bit more about next week for aeronautics and astronautics. And there's also competition teams. So here we are. Last year, we were the 2024 national champions on hydraulic bike team at the Fluid Power Vehicle Challenge. This is the National Fluid Power Association. There's me and Winnie, and then to my left is Rich. I guess to the left of the picture. And then here's the team. And we took 4 seniors, and actually I think this year it was 5 seniors and 1 junior. And the next year it was 4, it's usually 4 seniors and 2 juniors. And so there's lots of things you can do. We came in national champions, which was just awesome. There's aerial robotics, autonomous underwater vehicle, electric vehicle, solar vehicle, and Kennesaw Motorsports. If you're interested at all in working in the auto industry, Kennesaw Motorsports is the best way to go. Okay, so this is everything I talked about. And don't forget, we are on the first floor of the Engineering Technology Center. It's a really friendly bunch. Come by and say hi anytime. And we could pet Winnie if you want, ask some place. But if you ever see me in the hallway, I'm the one with the dog. Okay. So again, my name is Dr. Laura Rahala. My email is lruhala, LRUHALA @Kennesaw.edu. Thanks for your attention. Bye. This, and I'll stop recording.